True.
I have a question.
Oh,
Oh, no, you're first.
yes, sorry, okay, number one. Okay, number one, don't spend more than, say, an hour on it. I know. And if you don't get it, that's okay.
So I already spent that time, so.
Yeah. Yeah, because it turns out it is a big algebraic mess. And it's not my intention that you spend 5 hours on problem one. Spend an hour on it so you get a good feel for what's going on. And the first part of it should be able to knock out. And so, yeah, so that's what I'll say about problem one. And if you already spent your hour, you're done with problem one.
All right. Good for me.
And then let's make homework one or homework two due a week from today. Because
Yeah, we're covering soccer today, right?
yeah, well, because I heard groans when I said Tuesday next week. So a week from today, that's fine. Okay, Farrah, you had a question?
Yeah, for the kind of representation that we use for the polarization,
Which one?
all of them, the five ones. So is there any preference for using them or depends on the situation? And
Depends.
Depends.
Yeah.
And the other question is that I didn't understand what is the big delta. I mean.
Okay. So we have that. So we have the field representation, AX, AY, and delta, and we know where that comes from. You know, X component is AX cosine. Actually, let's do this. No, this is minus KZ. This is AY cosine T minus KZ plus delta. So that's our electric field, the two components. And so we see where AX, AY, and delta come from there. And then we have that tangent of psi is equal to AY over AX. And we said that, and then geometrically, that's just, we go out here, AX, and then we go up, AY, and then that's just psi. And then we said that we can represent the polarization state with this angle psi and with delta. And you can see psi has that information in it, has the ratio, and delta is just that guy. We could rewrite this and say, well, psi is psi, and this delta, let's just call it capital delta, just for the heck of it.
So the angle is same, right?
Same.
All right.
Yeah, but this is the notation that you usually see in ellipsometry, and we'll talk later about what ellipsometry is.
All right.
So that's the only reason why I bring it up now, is just so that you've seen it.
Thanks.
Okay, so we were talking about the complex number representation, which is tangent of psi, e to the j delta, or in other words, ay over ax, e to the j delta. And we saw how that meant that every point on the complex plane represents a unique polarization state. And we went through what the different points were. And then the last comment I want to make about that is that, in the ellipse representation of polarization state, so we have our ellipse, and let's say it's counterclockwise, whatever. This orientation angle, phi, we can relate it back to the complex number representation in that the tangent of 2 times phi is equal to 2 times the real part of the complex number representation over 1 minus the magnitude squared of the complex number representation. And similarly, sine of 2 times the ellipticity angle. And remember, the ellipticity angle, we can say that tangent of the ellipticity angle is equal to the ellipticity. And ellipticity is plus or minus b over a. And here we have a, and here we have b. So tangent of 2 times that ellipticity angle is minus 2 times the imaginary part of the complex number representation over 1 plus the magnitude squared of the complex number representation. So we can go back and forth between the different representations. Okay. So now what we want to do is look at yet another way of representing polarization state. And this is the Poincare sphere. And basically, if we take this complex plane where every point represents a unique polarization state, we can do a mapping and map it onto a sphere. And that is the Poincare sphere. So let's try to draw this a little bit. X, Y, Z, and we have some sphere here, and it's the unit sphere. And if we have some point on the unit sphere, and say call that point P, then we can drop a perpendicular down to the XY plane, and then we can come out here from the origin to where that perpendicular hits the XY plane. And then this angle is 2 times theta, 2 times the ellipticity angle, and this angle is 2 times phi, the orientation angle. So once we know the orientation angle and the ellipticity angle for a polarization state, we can map it to a point on the Poincare sphere.
So, is that Z in 3D? Is it not three? Does it have 3 coordinates?
Yeah.
Okay. And then the 2 delta is what angle from what to what?
2 delta, 2 phi,
The other one.
2 theta.
Theta. Sorry.
It's from the XY plane up to,
Oh, so it's
that.
like high. Okay.
yeah, well,
that-
so
in
it's
the-
going from this XY plane up
Okay.
to there.
That makes sense.
Now, it looks like spherical coordinates, but spherical coordinates are different in that you measure this angle, the azimuthal angle, rather than the angle from the plane. So similar to spherical coordinates, but not exactly spherical coordinates. Yeah.
This 2 theta, so just kind of to see if I'm following, is that 2 theta and 2 phi follow those 2 equations right there, which in turn is that theta in the ellipticity, and then that phi from that one, yeah?
Yes.
Okay.
That's right. Yeah, so phi is the orientation angle of the ellipse. Theta is the ellipticity angle of the ellipse. And geometrically, here's A, here's B, so that is theta. Yeah. Okay, other questions? Carlos, you have a question?
Yes, I don't know where. I'm trying to figure out where theta is on that ellipse.
Oh, so we come out A, and go up B, and, tangent of theta is B over A.
Mm.
So that means this angle right here has to be theta.
Oh, so it's the same theta for both.
Yeah, so that theta, that's the same thing. Okay. All right, so in the Poincare sphere then, we can write the x-coordinate of this point P in the following way. It's cosine of 2 times the ellipticity angle times cosine of 2 times the orientation angle. And then y is cosine 2 times theta sine of 2 times phi. And and z is just sine of 2 times theta. So it's easy to get the xyz coordinate on the Poincare sphere for a given polarization state. Now, let's think about what these, what a point on the Poincare sphere means. So we have the orientation angle and the ellipticity angle, and this is the unit sphere. So basically, what we get for a point on the sphere is the polarization state. The thing we don't get is the actual amplitude, because we're looking at everything in terms of sort of the ratio of AY to AX. So we throw away the absolute magnitude. We're just looking at the relative magnitudes of the Y and the X components. Now, if we look at this point right here and say, what polarization state does that point represent? Well, clearly, theta is 0. So this is 1, 1, 0. And phi is 0. So that's 1 and that's 0. So that gives us 1, 0, 0. So phi 0, that means the orientation angle is 0. Theta 0, that means the ellipticity angle is 0. Therefore, B is 0. So that just leaves us with A. So A oriented along the x-axis in this picture. So basically, it's linearly polarized light that is horizontal in orientation. Yeah.
I'm sorry, could you repeat that again?
So orientation angle is 0.
Okay.
Ellipticity angle is 0, so that squishes this to a line. But it's a line with orientation angle 0, so that means the temporal oscillation of the field is just back and forth here.
Oh, I see.
So that's linear horizontal polarization.
But you said it's linearly polarized at that point?
So this point represents linear horizontal polarization.
Oh, I see.
And as we go around the equator here, notice the ellipticity angle is 0 around the whole equator. If the ellipticity angle is 0, B is 0, therefore the equator represents all linear polarization states. And as we go around the equator, the only thing that's changing is the orientation angle. So we start off here, linear this way, and as we start going around, the orientation angle changes and just gets steeper and steeper. So as we go around over here, we get to about plus 45 degree linear polarization. As we get all the way to the back side, then we have plus 90 degree linear polarization. So it's linear vertical over here. As if we go around the other direction, then we're basically just rotating in the opposite direction here as we go around. So carrying out over here, we have minus 45 degree linear polarization. As we go back around, then we're vertical again.
And when orientation angle is 0, so that line comes on top of the x-axis, right? So
Yeah, this one, yeah, right here.
So then why you shouldn't draw it like this on top of x?
Well, so you draw it however makes sense to you. In my funny way of seeing 3D on a 2D surface, to me that's horizontal. You know, maybe it'd be better like that. I don't know, whatever. But it's supposed to be horizontal. It's supposed to be in the XY plane.
Okay, I mean that x is in this direction in your coordinate system, right?
What, this X
Yeah.
is this way.
Yeah, so when orientation angle is 0, then it should be on top of x.
Oh, no, this is,
She means pointing in the direction of X.
this is just,
Oh, this is a different coordinate system.
that's not,
The
that's not
upper
the
one,
same.
I'm talking, the upper one is
Yeah,
different?
different. So basically this is sitting right here and call it
Okay,
x
now
prime,
I'm
y
good.
prime.
Okay, perfect.
So it's kind of a local coordinate system tangent to any point on that sphere. Yeah, thanks for bringing that up. Okay. Any questions? All right, so I don't want to spend too much time on the Poincare sphere because we're not going to use it much. We'll use it a little bit, but not a whole lot. And therefore, I just don't want to spend a lot of time on it. But if we go to an orientation angle, or rather ellipticity angle, two times ellipticity angle, so that we're here on the North Pole, then that means theta is 45 degrees. Looking at this, 45 degrees means B is equal to A. And so that ends up representing clockwise circularly polarized light. Oh, I put the arrow in the wrong direction for clockwise. So in other words, up here, we have that in the upper hemisphere, delta is greater than 0, so we're always going to have clockwise orientation. And in the lower hemisphere, delta is less than 0, so it's always going to be counterclockwise orientation. At any rate, we go down to the South Pole, and we end up with the opposite linear state. And then as you go up any particular meridian, basically the thing that's going to change is not the orientation angle, but it's going to be the ellipticity. So as we go up this meridian, basically we're going to go from linear to, more and more until we get to circular. As we go around at a given latitude, then the ellipticity stays the same, but the orientation angle changes. So we basically take some ellipse, whatever it is for that ellipticity, and its orientation angle changes as we go around that latitude. So there's all kinds of interesting ways you can interpret what's happening in the Poincare sphere, but as I said, we just don't want to dive into it very deeply. Just be aware that you can represent polarization states in that way. What we want to do instead is go to Jones vectors, which are another way of representing polarization state. And we're going to use these a lot. And basically, we're going to define a Jones vector as a two-element vector, ax, e to the j, delta x, ay, e to the j, delta y. So that will be our basic definition of a Jones vector. And you look at that and you say, well, that looks pretty familiar. It's just this before I did the coordinate shift to get the x phase over here. And so, we could take this and we could pull out e to the j delta x, in which case then we have ax, ay, e to the j delta. Because remember, delta is delta y minus delta x. I could pull out the ax if I wanted to, so ax e to the j delta x, and then that's 1, and then ay over ax e to the j delta. And we look at that and we say, oh, that's just the complex number representation. We could choose to look at it that way. And we could also say, well, how does this connect back to an electromagnetic plane wave? And so an electromagnetic plane wave, before we wrote it as E of RT is equal to E naught, E to the J omega t minus kz, or E naught is just some constant complex vector. And this is a plane wave propagating in the z direction. And at one point we said, let's just change our notation here and call it an A, which led us to writing things this way. And basically all I've said here is, oh, let's change our notation again and let's call this J. That makes you feel good, right? We're changing our notation yet again. Okay. So yes, why the heck are we doing that?
There's no standard notation.
Yeah, that pretty much. It's just in Jones vector analysis, you tend to call that constant complex vector J as opposed to A or E naught or whatever. So let's just go with the flow and call it J. Okay. Now, the important thing, though, is for all of these symbols, they all represent exactly the same thing. And what's important to keep straight is what is the information that is in the symbol. And so, what information is in that symbol? Okay, so we can say that, yeah, I mean, you're absolutely right, Mark. Has the amplitude of x, amplitude of y, phase of x, phase of y. It's got those four pieces of information in here. We could repackage that in a slightly different way. We could say that it has the information of the absolute amplitude of the field, because the absolute amplitude is just square root of ax squared plus ay squared, right? It has the absolute phase of the field. If we look at it this way, in this one, delta x is the absolute phase. It also has the information of the relative amplitude, which is basically ay over ax. And it has the information of the relative phase of the y to the x component, which is delta. So these four pieces of information, we can think about it in this way. Absolute phase, absolute amplitude, relative phase, relative amplitude. Yeah.
Relative here, so if we were not in this particular coordinate system, what would relative mean? Like if it's
So relative just means the y component relative to the x component. So here's relative amplitude, the y amplitude relative to the x amplitude. Here's the relative phase, which is the y phase relative to the x phase.
okay.
And for polarization states, those are the only two things that matter. That's what specifies a polarization state.
So if we were in another coordinate, we need to transfer to a Cartesian coordinate system and then.
Yeah, in principle. Specific cases, maybe not. Because maybe we can think it through and not have to go to that trouble. So, in principle, yes, but in practice, maybe not. Okay. And when I say these two pieces of information are what's wrapped up in the polarization state, you can see that right here. You know, here's tangent of psi. Psi has to do with the relative amplitudes of y to x. And then delta is the relative phase. And so psi and delta, that's relative amplitude, relative phase. And similarly for all the rest of them, that's what it comes back to. Okay, so at this this point, we can say that often, but not always, we'll normalize the Jones vector such that the Jones vector complex conjugate dotted into the Jones vector is 1. And we do that when all we care about is the polarization state. And we just don't care about the amplitude or the phase. The overall amplitude or overall phase. If we're just trying to track polarization state, then often we'll use a normalized Jones vector.
Is that just to make it easy to compare?
Mm-hmm.
Okay.
Yeah, that's all. Yeah. Okay. If we have a normalized Jones vector like this, then and our complex representation of the field, we can write it as sort of the magnitude of E naught times the Jones vector, because it's normalized, e to the j omega t minus kc. So one of the things, just to be clear, a Jones vector, we always assume that the propagation direction is the z direction. So whenever you start to work with Jones vectors, that assumption is always implicit, which means that the electric field has only x and y components, since the electric fields are orthogonal to the direction of propagation. Okay.
And it's kind of arbitrary, right? Because you can always just decide that the direction you're propagating is z.
Yes.
Okay.
Yep, it's totally arbitrary. Yeah, so.
It just makes the math easier.
Yeah, exactly. Takes advantage of the fact that the electric field vector is orthogonal to the wave vector, and therefore you only have to track 2 components instead of 3. So if you can only track, if you get everything by tracking 2, then why bother tracking 3? Yeah, Carlos?
Sorry, that last notation at the bottom, you did that because it's normalized, right? So the J only contains the phase? Okay.
So the J only contains the relative amplitude, contains the relative phase, and actually, in this case, contains the absolute phase too. So I'm just kind of throwing all the possibilities up here without being too rigorous about it. Because we're going to do a bunch of examples, and you'll see what really matters and how that works. So let's do an example. Let's look at linear polarization. In that case, if we look at the xy plane, which is the plane orthogonal to the direction of propagation, so z-axis is out of the board, waves propagating out of the board. If we have linear polarization, then the electric field vector is just going to oscillate back and forth in a line, right? And we can say that that line is at some angle psi with respect to the x-axis. And so the Jones vector we can write down as cosine of psi, sine of psi. We can write it down by inspection. Because, and notice this is a normalized Jones vector. We're not worrying about absolute amplitude. But, this is cosine of psi, and that is sine of psi. And then delta is 0. If delta were if we had this instead, this state, then psi would be here. But remember, psi cannot be negative. So in that case, we would have cosine of psi, sine of psi, e to the j pi, which of course is just cosine of psi minus sine of psi. So that minus sign comes from delta being pi. Okay. Any questions? Yeah.
So you mentioned that the first Jones vector, that was a normalized Jones vector?
Mm-hmm.
Okay.
Yeah, well, just because if we take the magnitude of it, the magnitude's going to be 1. So it's automatically normalized. Okay. Now, very often we worry a lot about orthogonal polarizations. And we say that a polarization represented by Jones vector 1 is orthogonal to a polarization represented by Jones vector 2 if I take the complex conjugate of Jones vector 1 dotted into Jones vector 2 and the result is 0. Then the two states are orthogonal. And so if I wanted to find the orthogonal state to this, then let's say that that was J1, then I'd have cosine of psi, sine of psi, dotted into ax, ay, e to the j delta. I could subscript those with 2, but I'm just not going to bother. And then that's going to give me ax cosine of psi plus ay sine of psi e to the j delta. And that has to be 0 if the two are orthogonal. And so I have one equation and how many unknowns?
Two, because ax and y can become tangent to the side, right?
Yeah.
Or-
Yeah, that's right. Yeah, so I basically got two unknowns, delta and the ratio of ay to ax. I've got one equation, but really I have two equations because it's a complex equation. So I can take the real part and actually let me take the imaginary part first because it's easier. If I take the imaginary part, well that's real so it goes away. So I'm left with this over here, ay sine of psi times e to the j delta. I'm taking the imaginary part, so that'd be sine of delta. That's got to be equal to 0. Okay, so ay and sine are going to be something, whatever they are, so I can cancel them out. And that says that sine has to be equal to delta, or sine of delta has to be 0. So that means delta is either, by the way, what's the range delta can be in?
0
So delta can be in the range of
minus pi to
minus pi, and notice it can't be minus pi. Because then it would be degenerate because it would be the same as pi. So that means for sine of delta to be 0 with delta in this range, delta has to be either 0 or pi. But we don't know which yet. So now let's take the real part. And then I have ax cosine of psi plus ay sine of psi cosine of delta is equal to 0. Okay, ax, is it positive or can it be positive or negative?
positive or negative.
Positive or negative?
Did we say by convention it's just positive?
Has to be positive. Because if it's not positive, then we'll get an ambiguity in our phase. So ax has to be positive. Ay has to be positive. Cosine of psi, positive or negative? Can it ever be negative? No. Because tangent of psi is ay over ax. Ay and ax are always positive. Therefore, delta is always positive. Okay? So that means sine of psi also can't be negative. So positive, 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 positive. That leaves us with the cosine of delta. If I set delta equal to 0, then that's 1. Then I have some positives plus some positives equals 0. Can't happen. So delta equal to 0 is not a valid solution. So we have to have delta equal to pi. So delta equal to pi, then this becomes ax cosine of psi is equal to minus 1 times that, pull it on the other side, ay sine psi. So then we can do a little algebra. Ay over ax has to be equal to cosine of psi over sine of psi. Yeah, we can do that. Okay.
This just comes back to tangent.
Yeah. So at this point, I could say, well, to within an arbitrary factor, I could just say, well, let's just let ay be cosine of psi, and ax be sine of psi, and then that equation's satisfied. I know delta, it's pi, so I know everything here. So that means that J2 is going to be ax, which is sine of psi, ay, which is cosine of psi, and then I have e to the j pi, which is just a minus 1. And then comparing that to that, it's clear that if I do a dot product, it's equal to 0. So those are two orthogonal states. So if I take this guy and I plot him on here, then basically I'm coming out by sine of psi here, and then minus cosine of psi here. So it's this, which is orthogonal to that. Yeah.
So, in practicality, why would we want, is there a reason we want to know the orthogonal vectors?
Oh, big time. Big time. Yeah. It's not obvious now why it's important, but let me say why. So two reasons. If I have some arbitrary polarization state, I can always decompose it into a weighted sum of orthogonal states. I can choose any pair of orthogonal states, and I can take my arbitrary polarization state and decompose it into a weighted sum of those two states. That's, turns out, is so fantastic. And you'll get an appreciation for it as we go through the next lecture or two. Then the other thing is, if I have an optical system, let's say it's oriented along the z-axis, and I have some component here, whatever it is, leave it completely arbitrary. I have some arbitrary polarization state that goes in here to my system, and my system operates on that polarization state, and I'll come out with some other polarization state on the output, whatever it is. If this, well, generally speaking, actually, if this is, say, an anisotropic material, then the refractive index looks different depending upon the polarization state. But it turns out for an anisotropic material, I can analyze it and always come up with two eigenstates that do not change as they propagate through it. And those two polarization eigenstates are orthogonal, always. So that means if I take this and I decompose it into the orthogonal eigenstates of the material, by definition, the eigenstate propagates through with no change in polarization state. It just changes phase. So I can just figure out which phase each state picks up going through, then I can add them up at the end and easily get the output polarization state. So being able to take an arbitrary polarization state and decompose it into a weighted sum of orthogonal states, it turns out is crucial. You do it all the time in polarization problems, particularly involved with anisotropic materials. Okay, so let's get an idea of how that works. Let's define some orthogonal polarization states. Actually, let's do it over here. Okay, let's define L hat sub x as linearly polarized light in the x direction, in which case its Jones vector is just 1, 0. And let's define Ly as linearly polarized light in the y direction. And clearly, Lx complex conjugate dotted into Ly is 0. Pretty straightforward. So x and y linear polarization states are orthogonal. Similarly, if I had circular polarization in the clockwise orientation, if we go through and analyze it, the Jones vector, the normalized Jones vector, is 1 over square root of 2, 1j. So you notice that the magnitudes of the x and y components are equal, and you notice the y is 90 degrees out of phase with the x. Therefore, circular polarization. And then this is just normalizing. So, counterclockwise circular polarization is 1 over root 2, 1 minus j. So again, same magnitude for x and y components. Y component is minus 90 degrees out of phase with the x component. And remember, we have circular polarization when AX is AY and delta is plus or minus I hats. So these are the Jones vectors for those two cases. And then if we take clockwise complex conjugate dotted into counterclockwise, then we have 1 over root 2, 1 over root 2, and then we have 1 times 1 plus, and then we have complex conjugate of j, which is minus j times minus j, and that's just minus 1, and clearly that's 0. So clockwise and counterclockwise circularly polarized light are orthogonal states. Okay, so now let's have some fun with that. Let's decompose into orthogonal states for several situations. First situation is this circularly polarized clockwise state. Notice I could write it as 1 over root 2 Lx hat plus Ly hat, or J Ly hat, plus J Ly hat. Right? Mm-hmm. So what are we saying physically? We're saying that clockwise circular polarization is linear polarization in x plus linear polarization of y shifted by 90 degrees.
Makes sense.
Yeah, so it's a weighted sum of x and y linear polarization states. Similarly, I could take counterclockwise circularly polarized light and write it as Lx hat minus J Ly hat. And so it's just looking at counterclockwise circularly polarized light as a weighted sum of, or rather a sum of, x linear polarization plus y linear polarization shifted by minus 90 degrees. Okay, fine. Notice I could look at linearly polarized light in the x direction as 1 over root 2 clockwise circularly polarized light plus counterclockwise circularly polarized light. So I take this and add that to it, and notice I just get that. So x linear polarization is an equal sum of clockwise and counterclockwise circularly polarized light. I can interpret it that way. Similarly, Ly is 1 over root 2 clockwise circularly polarized light minus counterclockwise circularly polarized light. So take some clockwise circularly polarized light, an equal amount of counterclockwise circularly polarized light shifted by 180 degrees, that's the minus sign, add them together, you get y linear polarization. Okay, so we could play that game ad infinitum, taking any arbitrary state and decomposing it into a weighted sum of other states, orthogonal states. Any arbitrary orthogonal states, doesn't matter what we choose.
What if you did elliptical? Could you just weight x and y with ax and ay?
Yeah, with just weight one of these.
Differently.
Yeah.
Okay.
Or here, yeah. So yeah, you could weight, this with something, or you could weight that with something. You could weight them both, and then put the appropriate normalization factor in front. Yeah, exactly right. In fact, let's do that. Let's write down general elliptical polarization. The Jones vector for general elliptical polarization is cosine of psi, sine of psi, e to the j. And so if we draw the x and y axes, we're saying go out over here, cosine of psi, and then go up here, sine of psi, and then this delta, take this sine of psi and shift it by delta in the z direction. And that is general elliptical polarization, which lends itself to the following interpretation. You have some polarized beam, it's propagating in the z direction, freeze it in time, just take a snapshot. Look at the x component, the y component, in some plane. So here we've got them. And then delta is simply taking the y component and shifting it by delta, shifting it in the x direction. And how much do you shift it in the x direction? Well, it's just delta divided by 2 pi times wavelength. Okay, that tells you what fraction of the wavelength it is shifted. So this leads to my handy-dandy finger method of figuring out polarization states, which I'm happy to teach you, but you are under no obligation to use. But you can give me any polarization problem, And I can just stare at my fingers and move them around a little bit and tell you what the answer is. So, would you like me to teach you?
Of course.
Okay. So, whenever you're given a polarization state, and we're only gonna get the first piece of it right now. When we get to wave plates and other things, we'll see how you implement it. But whenever you get a polarization state, it turns out that phase, that's always the killer. Meaning that's always the critical thing. The relative amplitudes, whatever, they're not hard to deal with. But the phase, that is where the action is normally. So that's what I tend to keep track of with my finger method. My finger method is just stick a finger on my right hand in the direction of the x, positive x. Stick a finger on my left hand in the direction of positive y, and then just shift them by whatever delta is. If it's say pi halves, then this comes forward. If it's negative pi halves, this goes back. So let's say that we had this polarization state right here. So that's the same as saying 1 and 1 e to the j pi halves, right? Same thing? Okay, so I look at this and I say, okay, here's the x component, here's the y component, and I'm shifted forward by pi halves, right? So y comes before x by pi halves, and I'm not going to worry about the exact amount I'm coming for, I just know it's pi halves. So as that propagates towards me, what happens? First I see the y component, then I see the x component. So that means that the electric field vector has to rotate from here down over here. The sense of that rotation is what? Clockwise. And when delta is greater than 0, the sense of rotation is clockwise. So I don't even have to remember that delta greater than 0 is clockwise. All I have to do is say, okay, let's just take a test case. This is positive pi halves. Okay, so y hits my nose before x. That's got to be clockwise rotation. Done. So I don't have to even remember any rules. Okay, so we'll see how that's used when we get to wave plates. But you can always figure out wave plates very easily with that method. But yeah, and then, okay, we can address it then. All right, so any questions? All right, then let's summarize some of what we've done. And have a little picture of how it goes. Okay, so we have the field representation, AX, AY, and delta. We have the ellipse representation where we have the orientation angle phi and the ellipticity, zeta. We have the ellipse with the elliptical angle where we have the orientation angle phi, and then instead of the ellipticity itself, we replace it with the ellipticity angle, theta. And then we have the complex number representation, chi. And then we have the ellipsometric angles, where we have psi and delta, or psi and little delta, whatever. And we have the Poincare sphere, and we have the Jones vectors. So AX, AY, e to the j delta. Okay, now let's draw the XY plane and some arbitrary elliptical polarization state. say like that. It's not very good. Something like that. And then we have the semi-major axis. We have the semi-minor axis. And then this is the orientation angle phi. And then we have half the semi-major axis A, half the semi-minor axis V. And then we can do several things here. One, maybe I should do these in different colors. Over here, the greatest extent of this ellipse happens at AX, right? And the greatest extent of the ellipse over here happens at AY. So I could draw a box like this, which is 2AX and 2AY in size, that would fully enclose that ellipse. And if I were to draw that box, then this line goes to the upper corner of that box, and that's going out a distance AX and up a height AY.
Mm-hmm.
Therefore, that angle is psi. Because remember, tangent of psi is AY over AX. Okay. Now, alternatively, I could draw a box that fully encloses this, where that box basically does this. So the box is rotated and just barely fits the ellipse. And if I draw that box, then this upper corner, to get there, I go out a distance A and up a distance B, right? So if I draw a line here, from this blue line up to here, that's going to be the angle theta, the ellipticity angle. Because the ellipticity angle theta, or rather tangent of the ellipticity angle theta, is just B over A. Are we good with that, or do we have questions? We good? Okay. So now we have a geometric interpretation for all these different angles we've been talking about. So the orientation angle is kind of obvious. That's just rotation of the major axis of the ellipse. Psi is just, allow the x, up a y. What's that angle? And then the ellipticity angle is starting from the semi-major axis and go out a, up b, and then that angle is the ellipticity angle theta. Okay. All right. So, yeah. Okay. So I think at this point, what we'll do is Okay, let's do this. Okay, let's go back to our complex representation for a plane wave propagating in the z direction. So really this r, I should replace it with a z. So plane wave propagating in z direction. Then we can write that as, let's say, ax, ay, e to the j, how do we want to do this? Yeah, let's just do e to the jy here, e to the j x there. And then we have basically e to the j omega t minus kz. So this is not a normalized Jones vector, it's an unnormalized Jones vector. Okay, so then I can always pull out the ax e to the j delta x. And then that leaves me with a 1, and then ay over ax e to the j delta, and then e to the j omega t minus kz. And then I could actually, let me do this a little bit differently. Yeah, I don't want to do things this way. Let's take a different tack. Okay. No, I don't want to do it that way either. We don't have much time, so I'm trying to figure out how to do this quickly. Okay, let's do it this way. The complex representation of the electric field will look like the following. The electric field will have some magnitude, and I'm just going to give it some arbitrary symbol. I don't care what it is. Would you like to choose it?
D.
Which one?
D.
D? Like a capital D?
Yeah,
Dog? Okay. Lowercase d,
Yeah,
then that's
that-
going to
that means
confuse
electrical
us with
displacement.
differentials.
Oh, yeah, that's true.
Could
Let's
be
use C.
capital N for Nordine.
Maybe use C. Actually, let's use C for Carlos.
Carlos. Oh, Carlos. Okay, capital C. And remember, what does this represent?
Carlos.
Well, besides Carlos,
So there it is.
it represents the amplitude of the wave, or magnitude. Okay. Then in general, the wave will also have some overall phase. And what phase it has is dependent upon where the origin of the coordinate system is. If I change the origin of the coordinate system, I change the phase. And then the wave will have some polarization state. And then e to the j omega t minus kz. Okay, this polarization state is just a normalized Jones vector. Okay, so here's what I want you to get out of this. Any plane wave, it's always the same thing. You have an amplitude, you have a phase, you have a polarization state, and then you have the space and time dependence. End of story. That's always how it goes for a plane wave. So we'll make use of that when we talk about interference and a bunch of other things. Right now, in talking about polarization, we're really worrying just about that polarization state and how we're representing it. And what we're going to do next is the Jones matrix calculus, and that will allow us to figure out how to understand the operation of optical elements on the polarization state. So let's introduce that. So we've got 5 minutes, right? Okay. Yeah. Okay, so we'll introduce the Jones matrix calculus. And then we're going to spend a lecture or two on how to use it. So basically, I have some optical system, and I can represent that optical system as a series of elements along the z-axis. And then I have light coming in from the left, has polarization state, let's just call it, I don't know, J. And then each of these elements can, in general, operate and change the polarization state as it propagates through it, such that coming out, I'll have some other polarization state. Okay, the Jones matrix calculus basically says that I can represent the effect of this element on the instant polarization state with a 2x2 matrix. So let's call that matrix V1 for this element, V2 for that element, V3 for that, and Vn for that. Then the Jones matrix calculus says I can calculate the output polarization state as the matrix product of the input Jones vector multiplied by the matrix of the first element, matrix of the second element, matrix of the third element, etc., until we end up with the matrix of the nth element. So, what we want to do is figure out what are the Jones matrices for typical elements that operate on polarization states, and then figure out what the output polarization is for a given input polarization for some different possible combinations of those elements. So that's what we want to do for the next couple of lectures. And once we have that, then we can pretty much figure out any polarization problem. And we can do it pretty easily, because we just find the Jones matrix representation for each element, create a system matrix, which is basically just that matrix product, and then the effect of the system is just the matrix vector product of the input Jones vector and the matrix of the system, and then voila, we know what the output polarization is. So that's what we want to do. Okay, so you might ask yourself, what kind of elements here operate on polarization states? Well, there are a number of them. The first and most obvious is a polarizer that passes a given linear polarization state. This is also called a diattenuator. Another thing that operates on polarization is a retarder, which are also called wave plates, and sometimes called phase shifters, though I don't like that terminology. We're going to use wave plates for the most part rather than retarders. And then there are rotators that rotate polarization state. And this basically gets back to optically active media. We'll talk about what that means. And also can be induced by the Faraday effect. So we'll say something about that later. Okay. So in each of these cases, what we have to do is figure out what is the Jones matrix that represents the effect of that element on the polarization state. And as I mentioned, it will be a 2x2 element. I'm not going to derive it, but basically it will look something like this. So we need to figure out what those four elements are for these guys. And then what gets fun is when we take those elements and we rotate them. Because then we've got to do rotation matrices to keep all the coordinate systems straight. But it turns out that's really useful to do too. So ultimately what I'm going to do is show you how to take any input polarization state and get whatever polarization state you want out by a proper arrangement of polarizers and waveplates. And if you start off with linearly polarized light, then you don't even need the polarizer. You can just use a waveplate. And then we'll look at quarter wave plates, half wave plates. Once you can use either of those, then you have the whole game.
Do each of these assume some sort of linearity property like we talked at the start of the class?
Mm-hmm. Yeah, that's right. Yeah. Yeah, so in this case, it's all anisotropic materials. So we'll talk about those and see how they work.
What does the double underline under all of these mean?
It just means it's a matrix. Yeah, just like whenever we talk about a vector, like here, there's a line on top of the symbol. For a unit vector, there's a caret on top of the symbol. Whenever we write down a matrix, we've got to be clear that it's a matrix. So I'm using the notation of a double line underneath. You could use some other notation if you want, but that's what I'm going to use. But the point is, you have to pick a notation and stick with it. You can't just write down a bunch of symbols with no notation to show whether it's a vector or a matrix. Because, number one, it's sloppy. But number two, it will always lead to errors. So, and what's the point of deliberately using notation to lead to errors? I mean, that's just pointless. So, just use notation that keeps it all straight. Okay, well that's it. So, we will see you on